asymptotic notations. We did a lot of preparations. The main concept we introduced before we start this topic, the growth functions. The main thing we need to do, we want to compare growth functions. After we compare two growth functions, we want to describe the relationship between two growth functions in a compact way. Today we will do that. All right. D.1, introduction to asymptotic notations. First, we like to know why we need to use this kind of very special, very abstract notations, asymptotic notations. All right, so we look at the limits of two growth functions. Now, last time I gave you some examples. We compare, so we calculate the limits of the ratios of two growth functions. All right. Here, let us do some summary. Summary for those examples we did last time. In part B, part C, we did quiz questions. So part B, okay, all right. Limit of the ratio of two growth functions. When we consider that, what are the possibilities we may have? When we use the limit to compare two growth functions, we have these possible cases. We want to consider all the possible cases. Here, we summarize, we have these four cases. The first, the limit equals 0. When n goes to infinity, the limit equals to 0. Okay. Second, the limit equals some positive constant. Here, this c, although we can consider non-zero, but in our algorithm context, look at the underlying meaning of f of n, g of n, because we use these two functions to measure efficiency, right? And when we look at the efficiencies, we count the number of basic operations. Okay, so these two functions, we count the number of basic operations. So the underlying meaning is this, so we can assume the number should be positive. So for that background information, we can reasonably assume the C constant is a positive number, positive, real number. All right. The third case, infinity. And other than the above three, there is another case. It does not belong to any of the above three cases. We will see that. All right. So now discussion. For these four cases, we want to have some more discussion. For the first case, the limit equals 0. And we call the growth functions, right? We call f of n, g of n the growth functions because we use these functions to measure the growth rates of our efficiency functions. Yeah. All right. So then from the ratio, we want to compare which function grows faster, right? Yeah. So based on the limit results, we want to see the comparison results. Yeah. The comparison results should tell us which function grows faster. That information. So we need to give a conclusion. Yeah. Corresponding to case number 1, the ratio equals 0. Yeah. So you can see the denominator function grows faster, right? Yeah. Or you can use another way to express the meaning. The denominator function dominates the numerator function. Another way to represent dominates. Okay, yeah. Then we use a special term, order of growth concept. Order of growth concept. You know, if we use the order of growth concept, then our conclusion can be represented in this way. The order of growth of f of m is less than the order of growth of g of n. This way, the limit result can tell us this inequality result. Yeah. The inequality for what? For the comparison, for the order of growth of those two growth functions. Yeah. What we call order of growth? Yeah, you may wonder, why we call the concept, why when we measure how fast a growth function grows using this concept. Yeah, here, let me use a simple example to give you the idea, this order of growth idea a little bit. Yeah. Let us use some concrete example here. Yeah. This f of n, if I use a simple example n, yeah, just a simple n function. Yeah. And this g of n, let me use another simple function n squared. Okay, yeah. And definitely from the limit point of view, we have n over n squared, the limit equals 0, right? Yes. So matches our first case. Yeah. Then from the forms of these two functions, and this function, you can see both of these functions, they have the same form, n to the dth power. How about that? D is a positive number, okay? N to the dth power. Power function, yeah. They both in the form of a power function, okay? Yeah. When you compare two power functions, it's very easy, right? Yeah. So when we consider two power functions, n to the 8th power and n to the bth power, yeah, you can see easily, you just compare A and B, right? You just compare A and B. You can get idea quickly. Yeah, very convenient. The exponent numbers can tell us which one increases faster. Yeah. So here you can see in the polynomial or monomial. Yeah. So first, when the exponent number is an integer, it's a monomial, right? Monomial, polynomial, right? Yeah, it's that. And the exponent number corresponds to the degree of the monomial or polynomial, degree. Okay, yeah, all right. So that degree number tells us the basic information we need, or critical information we need. Okay, yeah, degree number. So that degree number, oh, actually, yeah. So here we use if we go back to the polynomial case, we use the degree concept in polynomial. All right, but for the polynomial, other than degree, there is another concept called order of the polynomial. Order of the polynomial. Yeah. So here, let me consider, a0 plus a1 n plus a2 n squared plus a3 n cubed. This case, all right. This is a cubic polynomial. Yeah. In this cubic polynomial, we say the degree equals 3, but there is another concept I didn't mention before. Yeah, here we have that. The order equals 4. Okay, order always equals degree plus 1. Degree plus 1. Yeah, that's the definition of order. Okay, yeah. So here you can see when we compare these two growth functions, basically we can compare their orders. Okay, orders. Yeah, because there is an original meaning for the order concept in polynomials. Yeah, but this order actually we extend from the polynomial order. Okay, the order, but we extend it. Yeah, why we extend it? Very simple. In the polynomial context, the order must be an integer, right? Must be a positive integer. Yeah, the smallest one is 1. The smallest order is 1 for a polynomial. Okay, yeah. 1, 2, 3 must be an integer. Yeah, but when we get to the growth function context, growth function not necessarily integer, right? Yeah. So our growth functions could be non-integer values. Yeah. So that's the reason we extend it. We allow the order of our growth functions to be non-integer positive numbers. Okay, yeah. So this D, only requirement is it's a positive number. Okay, yeah. So with this background, now you can see it is quite natural. We call order of growth of f of n and order of growth of g of n. And then that limit 0 tells us the order of the first one should be less than the order of growth of the second one. Okay, yeah. So that is the natural connection, yeah, between the limit view. Yeah. Here we take two views, the limit view and the order view, two different views. They are closely connected. Yeah. All right, so that's the case number 1. After you understand the case number 1, the remaining cases, yeah, we can understand just by analogy. Yeah. For case number 2, yeah, constant c, the limit, constant c, that c is a positive number. Yeah. So we can say both functions should have the same order of growth. Yeah, same order of growth. Yeah. So think about if the first one, you may have, let's say, 1/4 n squared. Okay. Yeah. The second one, you may have a n squared, right? Only their coefficient part different. 1/4 a, the numbers, the difference of these two numbers could be relatively big, but it doesn't matter. Yeah. Because the last time we cancel out that constant, right? So think about it. So last time when we consider f of 2n, the ratio over f of n, consider this ratio, that constant can be canceled out. Okay? Yeah. Yeah. So for that reason, even if these two constants are quite different, the difference is relatively big, but that's not important. When we consider order of growth, we ignore the constant part. Okay? Yep. We ignore the constant part. So we can safely say these two functions, they have the same order of growth. That's our case number 2. Okay? Yeah. So here, you need to adjust based on our background knowledge. You need to adjust the view to understand the relationship between two growth functions. Yeah, so that view is quite different from our usual view, usual comparison view. Yeah, our usual comparison view, these two functions, the difference is big, right? The difference is so big, all right? But in our algorithm view, if we ignore their constant coefficients, then they belong to the same category. So here we say they belong to the same category, n squared category. Okay? Yeah, same category. Then we put them together. Okay? So when we compare them, we say they have the same order of growth. Okay? Yeah. Yeah. So that's the, main adjustment we need to take in this order of growth comparison context. Okay. All right. Case number 3, similarly, the order of growth of f of n is greater than order of growth g of n. Okay. Yeah. All right. How about the case number 4? Yeah. The case number 4, why we have case number 4? You may wonder, right? Yeah. Because before I show you the detailed information for case number 4, can you imagine what is the possible case that belongs to, none of the previous 3 cases? Yeah. Because you may feel the first 3 cases should cover all the possibilities, right? You may feel in that way, but actually it's not. There is a possibility number 4, okay? That is, the limit does not exist. How do you know the limit exists, right? There is a possibility the limit does not exist. Okay, yeah. If you recall your calculus experience before, there is a possibility your limit does not exist. How about that? Okay, is that possible? Right? Yeah. But how to imagine, right? How to imagine Here, let me give you a simple example. The limit does not exist. Simple example here. All right. Let us consider these two simple functions. Okay, yeah. The numerator function, all right. Let me use 3 plus -1 to the nth times n squared. Okay. All right. The denominator function 4 minus -1 to the nth n squared. Okay. N squared can be canceled out. Yeah. But that ratio does not exist. Why does not exist? Yeah, because based on n even or odd, let's say n even first, where n equals to 0, that's even, right? 0, so that's 4, the numerator 4, denominator 3, okay? Yeah. When n equals odd, the numerator 2, right? Yeah, odd, 3 minus 1. So that's 2 over denominator 5, right? Yeah. 2, so you switch back to the previous pattern form, 4 over 3. Another time, alternatively, yeah, these two numbers change, alternatively, that's the pattern. When a sequence takes this special pattern, do you think the limit exists? It does not exist, right? Up and down, yeah. It never converges, yeah. So we say the sequence diverges, right? Diverges and not converges. Okay, it does not converge. Yeah, diverges. Yeah. In this way, the limit does not exist. All right, the limit does not exist. What does it tell us? Yeah. It tells us the limit way does not work for order of growth comparison in this way, all right? Yeah. But if we change to a different way, then probably we can get a comparison result. It just tells us the limit way does not work. It does not tell us there is no way we can do the comparison because we have other non-limit way to do the comparison. Yeah, we will see that later. All right. Now, the conclusion for this discussion. Okay. All right. Oh, yeah. So here, so here we need to use some compact notations. Yeah. Because look at here, case 1, 2, 3, 4. If our conclusions like what we did here, 1, 2, 3, 4, not that compact, right? We need to write a lot of words here. Yeah. But we want to have much more compact expressions that we need. The expression is, yeah, the first case, f of m belongs to little o of g of n. Little o. Yeah. Yeah. The special thing is little o. Okay. Now, what's the meaning? Yeah. Because the first time when you see it, you may ask, what's the meaning of that? The meaning is the limit of f of n over g of n equals to 0. That's the meaning. Okay. But we don't want to write in that, relatively more complex way, okay? We want to write in a relatively simple way, that this is the simple way. Yeah, okay? All right. If I use a little more words to explain this little o of g of n, that represent a set of functions, a set of functions. Okay, the meaning is a set of functions. What are those functions in this set? For all those functions, when you take the limit, one of those functions over g of function, you take the limit, that limit goes to 0. Okay, so you put all those functions in one set, and f of n belongs to that set. That's the meaning. That's the meaning. Here we use the set view. Yeah. Here in this expression, we use the set view. Okay, set view. Okay, yeah. All right. Similarly, for other cases, we have the similar notations. Second one, f of n belongs to big theta of g of n. Another set this time, big theta of g of n, another set. Okay, yeah. The third case, f of n belongs to little omega of g of n. Little omega of g of n. Yeah. Okay. Here, these three notations, little o, big theta, little omega, these three notations, we call asymptotic notations. Okay, compact way to represent the relationship between two growth functions. All right, yeah. Now, that's the three of the asymptotic notations. We have a few more, okay, a few more. Yeah, all right. We will see a few more later. Yeah. All right. Yeah. But for case number 4, we cannot. So at this point, we cannot represent using the asymptotic notations. Yeah. Yeah. Because we do not have the comparison result. Okay. We do not have the comparison result. So we need to try a different way for comparison. Okay, yeah. So we need a new method for case number 4. Yeah. All right. So the new method